Hi, thank you for having me here, and thanks for sticking around. This talk is about applying traditional approaches to causal inference, and specifically applying theory of semi-parametric estimation to effects of interventions on a community where we also have a community connected by network. And we're not going to bother with the estimation or performance doing statistical modeling of the network. We assume that the network is known and fixed, and all estimation is conditional on the network information. And we hypothesize that there's a community, we have a network, but most importantly that intervention received by each individual has an effect on other people's outcomes. So hence, that's how network component figures in, and I'll make it more precise in a second, what I mean by that. But it's been known, obviously, that such type of interference or spillover induces dependence between units, and that leads to dependence. So, and that traditional approaches to inference that do not adjust for this dependence would be biased and specifically anti-conservative. So our main goal is to establish a semi-parametric framework for estimation of these types of effects that we think can spill over from one unit to the other. We also want to perform correct inference, and also I'll advertise the two packages, one TMLnet, our package that performs these types of estimation in dependent data, and also SimCausal package, which I won't have time to go over, but it allows for simulation of synthetic populations with these types of dependence, specifically for causal inference applications. So first we'll review the classical IID setup. The simplest possible way it's presented, we will have study of n IID units, and for each unit we collect some baseline covariates, we observe the exposure, which is binary, and we also record the outcome. Okay, and we say that each unit is generated from some unknown distribution, the adjoint distribution P0, and we can factorize our likelihood in the following manner, where we take the conditional distribution of the outcome as one factor, conditional distribution of the exposure is another factor of the likelihood, and the distribution of the covariates. And in our model, we do not want to make any specific assumptions about the distribution of the conditional distribution of the outcome or distribution of the covariates, but we might use some knowledge about the exposure mechanism. For example, if we're in a situation with a randomized trial, we might actually know what the distribution happens to be, or not, if it's an observational setting. And we'll be specifically focused on the parameter of this distribution. It's a functional that takes a particular distribution, or this one, and maps it into some number. And in this case, the number is simply the average of the mean expected outcome across all units, where we set the exposure to 1. And it's a parameter of the data. And the nice thing about it is that it also has some causal interpretation. If you're willing to believe in certain causal models, it's actually a counterfactual outcome in my population if I, contrary to the fact, set everybody's treatment to 1. However, it requires additional assumptions, and even without them, it's still, I argue, a perfectly interpretable parameter, and it's a statistical parameter of the true data generating distribution. All right, so what do we mean by dependence now? We have ID units, and to be more precise, for 2 units, 1 and 2, we assume that unit 1 is friends with 2. And to make it explicit, we're assuming that the exposure of unit 2 may have an effect on outcome of unit 1. And that's depicted by drawing an arrow. And I'm not saying that it necessarily that the exposure of unit 2 has an effect. We're simply hypothesizing that there might be a spillover effect, and we want to include it in our framework, meaning that we want to estimate the effect of that other unit's exposure on the outcome. Now, let's go further. We can also assume that the baseline covariates of unit 2 have an effect on the outcome of unit 1, and same thing with baseline covariates of unit 2 has an effect on the exposure. And finally, we can also assume that their baseline covariates might be correlated, and we're not specifying the directionality of this correlation. We're just simply saying that they are correlated by drawing a double arrow. So essentially, we drew all possible kinds of dependencies that might occur between 2 units. And of course, if the friendships were symmetrical, if we assume that they're symmetrical, we'll have to draw the arrows in the other direction as well, from unit 1 to unit 2. That's what we mean by dependence. Now, let's make it more formal. Our data is as before. We collect data on baseline covariates, which I now denote as vectors. So we denote the W bold as all the n baseline covariates. Same thing with exposure. Bold A is all the n exposures on n units, outcome. And our data is on all n units is generated from some unknown distribution P0n, and n is to signify the fact that it's a joint distribution for all n units. Since they're dependent, we cannot view it anymore with this IID framework that I previously described. So it's one joint distribution, and the network plays into here with sets that are called Fi. And we assume that for each person, we record a set of friends. Those units are the units that the unit I can receive input, as I just described on the previous slide. So we observe this network. The entire collection of these sets on all units is referred to as network profile. And we make some assumptions that this set's are bounded by some, the size of the set is bounded by some universal constant k. And we can also relax that assumption by assuming that this k goes to infinity, but as long as k over n goes to 0. And this is what I learned in this workshop referred to as a sparse network. OK, so we observe a single draw of this O from some unknown distribution. And now the analog for the previous treatment effect, when we set everybody's exposure to 1, would be this, where we have to estimate the conditional expectation of outcome y for one unit, conditional on all covariates of the unit, as well as the covariates of the unit's friends, because now they essentially become confounders, so we have to adjust for them. And we also want to estimate the effect of the exposures of all units of the friends. And we then average this parameter over all n observations. Now, if the network is very small, you might get away with this. But in any realistic network situation, this is not an estimable parameter because of dimensionality issues. So that immediately brings up the issue that we have to deal with, and it's the first assumption of the framework. We have to deal with the curse of dimensionality, and we're going to do it by defining summaries. We're going to find summaries of the data where we say that the outcome, yi, really does not depend on all exposures of their friends and the covariates of their friends, but rather it depends on some summary measure of those exposures and the summary measure of those baseline covariates. And we leave those summaries undefined, but we only require that they have the same dimensionality across all units, and that they map in the common space also across all units, which would suggest that we can actually now estimate this conditional outcome model by pooling across observations. And we can also summarize our data in a very succinct way now by simply replacing the baseline covariates on unit I with the summary of the baseline covariates and the exposure with the summary of the exposure, and we'll refer to this AIS as the effective exposure, meaning that it's the exposure that is effective for this unit I that summarizes all I need to know about the other people's exposures. And we can also rewrite the parameter that we're interested in a more succinct manner, where we simply want to estimate the conditional expectation of the outcome on the mapping of on the summary mapping, where we set everybody's exposure to 1. Okay, and of course adjusting for the baseline summary. We have to make more assumptions to actually be able to learn this distribution for all n units. We assume that conditional on some summary values, that all yi's, the outcomes, will be sampled from the same distribution. That doesn't mean that they're all sampled from the same distribution for all units. It just means that when we condition on the same values, they would be the same. So meaning that there is a parameter, common parameter, that will allow us to identify the outcome model, the conditional outcome model. Same thing with exposures. We assume that they are drawn from the same common distribution when conditioned on the same value of the summaries. To say it in words, essentially, it means that if I and j have the same covariates, and if they have the same number of friends, and if their friends also have exactly the same covariates and exposures, then these two outcomes will be drawn from the same conditional distribution. Of course, I'm not being fully honest here because I just defined the summary measure, so it's really not the covariates and exposure, but it's a summary of the covariates and exposure. But in a most non-parametric way, you could, we're not restricting the summaries, or you could easily define the summaries as just simply listing all the exposures of friends and all the Bayesian covariates of friends, but as I just argued, with any realistic network size, this is non-feasible, so we have to make some kind of assumption. And this gives us the likelihood of the data where we have conditional independence of yi when we condition on the summaries, the effective exposure in the Bayesian network summaries, and the same thing with the factorization of the exposure mechanism based on the baseline network summaries. And we're not making any assumptions at this point about the joint distribution of the W's, so we're simply saying it's the entire joint distribution of the W's is a single factor of this likelihood. Okay, so now we have one more thing before we can actually fully define the parameter and proceed with estimation. We will, even though previously I was talking about an intervention that sets everybody's exposures to 1, we're going to be more general than that. Our intervention of interest will be a stochastic intervention called G star that describes some known random distribution that assigns exposures to all n units. Of course, it includes all possible static interventions, but it also allows us to, and it simplifies the notation, but it also allows us to use actual random interventions that might have more support in the data. So in causal inference terminology, this would allow us to avoid positivity violations. Now we can define post-intervention distribution, where we simply replace the factor of the likelihood that was responsible for exposure mechanism with this new stochastic intervention G star, and it's referred to as post-intervention distribution, where we have new random variable O star that's generated from this distribution. And we can also generalize this framework, but I won't get into that too much, but we can generalize this to actually define our stochastic intervention by a collection of I-specific interventions, G star Fi, where each G star Fi defines an intervention for the individual and I and their friends. Same thing for another unit, G star Fj would define an intervention for J and friends of J. It's important because this type of intervention, so we have a collection of n of these interventions, and they might not be compatible with a single intervention that would assign certain exposure to the entire population, meaning that there might not exist such an intervention. Nonetheless, it's still a perfectly valid parameter, and it's identifiable. Most importantly, though, this parameter allows us to get at the peer effects and indirect or direct treatment effects, where we, for example, want to know what's the effect of the intervention on only me if I were to keep the exposures of my friends constant. Or vice versa, we could keep the exposure of unit I constant, and we might be interested in to know what's the contrast of assigning exposure of all my friends to 0 versus 1, and do it for everybody and average. So that's kind of a version of indirect treatment effect and version of spillover effect. Okay, now we have one more step. We need to define the conditional expectation. Or we'll introduce new notation that defines conditional expectation of the outcome as Q bar. And we are ready finally to define our parameter, which is simply the expectation of our post-intervention outcome, where we replaced the exposure mechanism with our stochastic intervention G star, and we simply integrate the conditional expectation of yi with respect to all possible realizations of our exposure that are governed by this stochastic intervention. So if intervention really is just static, this becomes degenerate, and we only need to integrate this with respect to the distribution of the W's. This is our parameter. It's a function of the likelihood, and the important part of this is that it actually turns out that the typical ID maximum likelihood approaches will work for estimation of the factors of this likelihood, specifically these factors. And the intuition for that is sort of a little tricky, but The point is that you can marginalize your likelihood with respect to the summary measures, and you obtain a likelihood for the summary measures yi, AIS, and WIS. You can then take the mixture of these likelihoods, and you obtain a mixture distribution. Now, you can also think of a random variable that will be sampled from this mixture. And it turns out that the parameter that we just described can be succinctly expressed as just simply the expectation with respect to this mixture distribution, where we're replacing our mixture exposure model with a particular stochastic intervention. That's also a mixture, but it's a function of the original stochastic intervention. It's convoluted, but the point is that the usual log likelihood loss function that's used in maximum likelihood estimation turns out to be a valid loss function for the factors of this likelihood. So it's a valid loss function. It doesn't necessarily prove everything else. We don't have optimality rates for it, but it does seem to work really well, even though the observations are clearly dependent when you're performing this maximization. Now we can actually go about estimating this parameter, and we're going to use targeted maximum likelihood. So this is not a cookbook. It's more like a collection of facts about targeted maximum likelihood, and it's a bastardization of the very elegant theory of semi-parametric efficiency. But the basic underlying concept is that we're interested in substitution estimators. That is an estimator of the likelihood and a mapping that I just described. So if you give me an estimate of the likelihood, I can apply my mapping to it and obtain the estimator. That's a substitution estimator. And well, if our model, the p theta, is finite, then the theory tells us that maximum likelihood cannot be beat. So we're done. Unfortunately, that's not our model. And most often, to estimate the factors of our likelihood would require certain smoothing. For example, if we need a density to estimate our plugin, to get our plugin estimate, might require estimation of the density as part of it. That, or for example, our data might be highly dimensional, and it is well known that kernel density estimator, for example, will not have the root n parametric rate, and when we apply the substitution estimator to that, it will inherit all the bias and all the issues. So it may not converge at the root n rate, and essentially what TMLE does, the whole point of it is to fix this estimator by considering the least favorable parametric submodel through initial density estimate Pn, and if you pick that model in the right way, it retains the first order optimality of the estimator. Because after all, we didn't care about estimating this whole likelihood, and we didn't care about estimating Pn. We only did it so that we can obtain our final estimate, and that's what essentially TMLE does. It's actually can be applied in a much more general way, because we don't have to be estimating the densities. It can be applied to any bounded loss function. So in this case, notice that our parameter depends on the Q bar, which is the conditional expectation of the outcome, and the distribution of the joint distribution of the W's. So if we ignore for a moment the issues with estimating the joint distribution of the W's, we know that we only care about estimating this conditional expectation, which could be a conditional density if the outcome is, for example, continuous, or it could be just binary regression problem. So we can do exactly the same trick. Rather than defining a parametric model through the entire density, we define the parametric model through our initial estimate of this conditional expectation, which is given by this simple model. It's parametric in epsilon. It uses logit and expert transforms just so that simply we can retain the same bounds from 0 to 1. And we will maximize, we will fit this model given the initial estimate by maximizing with respect to epsilon using maximum likelihood estimation, and we will define a very specific loss function. And that's really the key. And that's the score of this loss function has to solve the efficient influence curve, which would fix our estimator. This is, again, bastardization, but the intuition essentially is there. You can define the scores. If you define the scores in a smart way, your parametric submodel will recover the convergence rates of the estimator and its optimality. OK, so now that we have obtained, once you fit the maximum likelihood for this epsilon parameter, you can simply update your initial model estimate with this Q and star and do a substitution estimator. And again, TMLE is not the only, TMLE is not the only approach that allows to do this. However, it's one of the few that, or the only one I know that is also a substitution estimator and not ad hoc. Okay, and this is now our parameter estimate. The TMLE is simply the plug-in estimate with our fixed Q1 star, the conditional expectation of the outcome, and the stochastic intervention. All right, so now a little bit of a promotion. The TMLE net R package implements 3 estimators for the dependent data. And the first one is the Horvitz-Thompson estimator, or also, as it's known, inverse probability estimator, which essentially reweights each outcome by the inverse probability of the effective exposure, which effective exposure is the summary of all the network exposures. And G computation estimator, it simply integrates the outcome model with respect to the initial estimator of the conditional expectation that is not targeted. And then the targeted maximum likelihood estimator takes those, essentially uses those 2 estimators to recover the central limit theorem, given that you have good enough control over the second-rate terms. And that's an issue of its own, but outside of the scope of this talk. And importantly, that it also performs 2 approaches to inference with dependent data, and I will have time to describe one of those. And it will work with independent data if there is no network. All right, let's take an example of how we actually use the package to define these summaries. So the syntax is pretty straightforward. Suppose we want to define a baseline summary of the 2 baseline covariates, W1, W2, where we take the product of W1 and W2 for all friends of each observation, and then we sum them. So the syntax is sum, and we use double square bracket to index all the friends of each observation, and Kmax is a variable that automatically evaluates. And if Kmax is the maximum number of friends for anybody, and if the person does not have that many friends, it's just zeros. So that's the baseline summary. With exposure summary, we can do very much the same. We define the effective exposure as the 2-dimensional variable, which is the person's exposure, A, and also the sum of the exposures of all the friends, which is just double square bracket A from 1 to Kmax. And now, important point is that, as you already see, that even if the exposure itself is binary, the effective exposure, the AIS, is likely to be continuous. And TMLNet implements a conditional histogram estimator to essentially partition the range of the continuous variable and fit the conditional model to each individual partition, then reconstruct the prediction. And it all happens automatically. And at this point, it's only based on the logistic regressions. But the whole idea is that why we're doing all this hard work is so that we can use non-parametric or flexible estimators to fit these the outcome model and the exposure model. But those things are not implemented yet. For example, ensemble learning is one of the ways. Similarly, we want to define an intervention now, and these are different examples of intervention. For example, we might want to be interested in the intervention that sets everybody's treatment to 0, in which case you just simply say A is 0. You might be interested in an intervention that says takes everybody's exposure and takes 1 minus that exposure. This intervention doesn't make any sense. It's just simply to showcase that you can use the covariates to define a specific intervention. Similarly, with the stochastic interventions, you can define a distribution, the G star, that would sample each individual exposure according to some probability distribution. And on top of it, that of course it can be arbitrary distribution, and it can also depend on baseline covariates, as I showed in the last example. And after you define the intervention, we still need to reevaluate the effective exposure as defined in the previous slide. So after you define the intervention, the effective exposure is reevaluated for all observations. And then we can actually proceed with estimation. All right, the hard part is inference. Well, we need to capture variability between different dependent observations. And bootstrap will generally not work, just because if you bootstrap, it will estimate the variability as if the observations were independent, so it will be severely underestimated, dependent on the level of dependence. Now, we make an additional assumption referred to as weak dependence, where we say that each baseline covariate depends only on a finite number of other baseline covariates, which is k at most. And remember, we bounded our friend sets by k, so this is where it essentially comes from. Under this weak dependence assumption, we can prove asymptotic normality of our TMLE estimator, and of course, under certain conditions on the second arrow terms. And the asymptotic, the limit in variance is expressed by this operator, which is, I'll go in a second about what is the expectation, but the sum, it's a double sum over all observations that are dependent, for whom these influence curves are dependent. And I'll show the influence curve in a second, but it's a limit of this double sum. And the indicator Rij is 1 when the friends have, when I and J have friends in common. Okay, so the efficient influence curve that I was talking about is this. It's ugly looking, but the main component of it is this first part, which involves the inverse probability weighted estimator for our effective exposure, and also the exposure model under the intervention G star. And it also involves the outcome and the outcome model, the conditional expectation of the outcome. And basically, we need to evaluate this for every observation. So, and then we need to plug it in here and hope for the best. Because we really cannot evaluate this expectation. We only have one di in the data, and we only have one dj in the data. And then we need to sum it over all I and j. So another important thing to point out is that this efficient influence curve is double robust estimating equation, meaning that if you actually went about estimating your parameter by just simply solving this, plugging in all the estimates in all the components that are unknown, and then solving it for your parameter, you would have double robustness property, meaning that if you estimate your exposure model correctly, or you'll still be consistent, even if your conditional outcome model is wrong. Similarly, if you estimated the conditional expectation of the outcome correctly, the model for Q bar was correct, but the inverse probability weighted estimator was wrong, this estimator would still be consistent. And this essentially provides the motivation for TMLE, because by doing this trick for fixing the estimator, it ends up solving this equation. So TMLE will be also doubly robust in that sense. And finally, so to get the variance, we simply plug in all the estimates on this I-specific influence curves, and we do the double sum. And as I said here. And then we evaluate essentially the empirical analog of this asymptotic variance estimator. Now the problem is that even under our weak dependence assumption, this estimator, as far as we know, is not identifiable. Unfortunately, I don't have time to go into it. But if we were to assume the IID model for our baseline covariates, meaning that all baseline covariates are sampled as IID, then everything works great. But we don't want that, and because I mean, the whole point of this network was that there is dependence. So we don't like that assumption. There are possible ad hoc approaches. Essentially what we need is that we need to evaluate this component of the efficient influence curve for I-specific observations. And since we're not making any assumptions about the model on the W's, we're putting the mass 1 on all of the W's. That's our estimator, which makes this whole component 0. And unless there's some way to sample from the W's that is sort of not ad hoc and would work in all possible cases, we'll be able to estimate that, but we're not aware of such approaches. A possible solution is to simply go with the conditional parameter. We're conditioned on all the W's, which changes the interpretation. So before we're estimating the counterfactual outcome in a network where we assigned everybody exposure to particular stochastic intervention, now we'll be estimating the counterfactual outcome among everybody with this set of covariates, which is different. And the inference works if you change your parameter to this, but of course the variance will be much smaller, but the interpretability is also lost. All right, and you can prove under all these assumptions, you can actually prove that this variance estimator will converge if you can sort of ignore all these minor issues. And I'll just quickly go over the simulation in 1 minute. This simulation is here to essentially show how badly things can go if you completely ignore the variance estimation. The focus on this slide where we have dots, and this is the coverage of the 95% confidence interval that's based on 3 different estimators. The yellow dots are the variance estimators that assume the data is IID, and the sample size increases from 500,000 to 10,000, and different estimates are essentially different parameters. We're doing stochastic intervention, we're doing dynamic intervention, network intervention, or combination of these, and basically we're seeing that it's really bad if you ignore the dependence, and that's my conclusion.
Do we have any questions? I have one question while I'm getting set up. It's just in the case that there's a time series of outcomes, one of the types of dependence that you didn't consider is where YIT depends on YJ T minus 1.
Correct. Yes. So
which could generate some longer range dependence, right?
Absolutely. So that's one of the main criticism of this framework has been the fact that the assumption of independence of the outcomes is unrealistic. For example, when you have a process over time, which is actually the case for most networks, even when the network itself is static, the outcomes generally happen over time, and the dependence over time grows. So you have to adjust for every single. So one way to sort of deal with this assumption is to actually collect more data. We have collect those outcomes at different time points, and then you could redo the whole theory of the whole TMLE and the whole framework that I just described, but it becomes intractable computationally very, very quickly. And only recently we had some ideas how to actually, basically what you need to do is derive the efficient inference curve for each of these time points, and it's a difficult problem. But we're working on it.